Hi everyone, we'll just wait a few more minutes for a few more people to turn up and then we'll get underway. Okay, welcome everybody to this latest in the DARA e-seminar series. We've had a bit of a break, bit of a hiatus, mainly due to the sort of northern hemisphere summer, but now we're kind of back, and there's a good program of e-seminars coming up over the next few months that Trish and I have put together. I hope everyone's still well. It's good to see so many old friends back on the participant list. Yeah, it's good to see people continuing to engage with all things DARA. The situation with the project is kind of as we left it before. We're still waiting for an extension to the project, so it's still a bit of uncertainty there, but we're hoping to resolve that soon so that we can get on with planning our next endeavors. So, coming to today, it's a real pleasure to introduce Professor Mark Thompson. Mark and I have been partners in crime in this endeavor for a very long time.
Serious crime.
Serious crime, yes. Both in terms of DARA itself, so Mark has been very instrumental in supporting DARA over the years, right there at the beginning. So he will be familiar to many of you as a Unit 1 lecturer for Zambia in the early days, and more recently he's been transferred over to Madagascar because he wanted to improve his French as well as his astrophysics. And so, yeah, Mark's been central to DARA for the whole time. Today we're obviously more focusing on his science interest, and there we also have overlapped for a very long time. So I think it would be true to say that between Mark and I, we probably dominate radio surveys of the galactic plane these days in world astronomy. So so it's a real pleasure to introduce him giving a talk on the latest of these, and of course this or working up to the latest of these, because I'm sure Mark will mention the MeerKAT survey of the galactic plane. And so, you know, this is really our first chance to start interacting in earnest with data coming off the newest telescope, and obviously the first real frontline radio interferometric array on the African continent, and of course a key forerunner to the SK itself, which of course we're all looking forward to. So I think without any further ado, I will hand over to Mark. As usual, the situation with these, if you've got any questions that you think of during the talk, then just pop them in the Q&A window rather than the chat window, okay? And we'll deal with those at the end. Okay, so I'll hand over to Mark.
Okay, thank you, Melvin. Right, so let me share my screen. Okay. So can you see that now?
Yeah, that's fine.
Brilliant. So it's a pleasure to give a seminar to Dara. It's I have to say it's slightly strange for me. This is the first seminar I've given where I'm sitting in a room in my house talking to myself, but in reality you can all hear and see what I'm doing. So what I wanted to talk to you about this evening is the Radio Milky Way, and what the Milky Way looks like in radio wavelengths, and give you a little bit of a historical perspective of what we've been doing. I say we, I don't mean me or Melvin. We didn't start this in the 1930s, so we've built on the shoulders of giants. I think that's probably the right thing to say. I will talk you through the Radio Milky Way, and as Melvin said, I will show you some of the results from the newest radio telescope, MeerKAT. And that's what we can see on this very first slide. This is the MeerKAT image of the galactic center, and I will come back to this a little later. Okay, so just a little bit of a recap about the Milky Way. I'm sure you all know, but let's just get an idea of the geometry. So on the left hand here, we can see what the Milky Way looks like when we look at it from the ground. We see kind of a band of light and dark regions in the sky, which are stars and nebulae and molecular clouds. But what we're actually doing is, if you look at the image on the right, this is a top-down view of the Milky Way. It's an artist's impression because we haven't been able to go outside the Milky Way yet and look at it from the top down. And in this artist's impression, the sun is located here, sort of towards the bottom. What we're actually seeing is we're looking through the disk of the Milky Way. The Milky Way is a flattened spiral, and we're looking through the kind of the central axis of the Milky Way, which is why when we see it on the sky, it looks like a flattened a band of light on the sky. One of the things to take home from this is that when we're looking at it with visible light, we see the stars, but we also see lots of gaps in between the stars and lots of dark clouds. And that's because in visible light, we can't see all the way through the Milky Way. If we use radio wavelengths, as we'll see, we can see all the way through to the edge of the Milky Way if the radio telescope is sensitive enough. So if we want to take a census, for example, of star formation throughout the Milky Way, then the radio is the right place to do it. Okay, so what I'm going to tell you about is really how we got from here on the left-hand side. This is the very first image of the Milky Way, radio wavelengths by Reber in about the 1940s, and you can see this very bright region here, Sagittarius. This is the center of our Milky Way Galaxy. And if we fast forward to 2019, 2020, this is what on the right-hand side. This is what we can see now with MeerKAT. So we've gone from seeing 3 blobs on the sky to absolutely fantastic detail and lots of different structure in this galactic center image, from Sagittarius A star, the center, all of these weird filaments that nobody really knows what they are or what the physics of them are, to supernova remnants, exploded stars, and we see the remnants of the supernova explosions. So what I'm going to go through is really in Milky Way radio studies, how we've gone from the beginning with very, very early images, and some of them weren't even images, I have to say, to the present day, and with a little bit of a look to the future and work that's happening right now. Okay, so just to give you some limitations of things that I'm not going to do. I can't put 70 years of radio astronomy into one seminar. I can't even put all the science into one seminar either. So I'm going to mostly talk about continuum work. So broadband studies of the brightness of the radio waves. I'm not going to look at spectroscopy, so I'm not really going to talk about H1, neutral hydrogen, masers, molecular lines, absorption lines. They could each be a seminar just by themselves. So I've left them out. I quite like it, not having to deal with H1, it's quite good. I've also skipped out some of the surveys and some of the Milky Way studies because, again, you just can't have everything in a seminar. And you'll all be very glad to know that I've kept this down to only 2 equations, and none of them are differential equations. So if you're looking back at this as a complete survey of the field, it's not a complete survey of the field. And there's lots and lots of projects that I've had to miss out just for time. So I haven't talked about, for example, the surveys of the Milky Way with the Molonglo telescope in Australia, or the Australia Telescope Compact Array SGPS survey, which was H1, or the GALFA survey, which is again another H1 survey, or Thor, which is an H1 and recombination line survey, or Scorpio, which is a recent survey with the Australia Telescope Compact Array, and is an important study as a precursor for SKA, but unfortunately I've not had a lot of time to mention it in this talk. So this is sort of like a personal journey where I've selected the high points, and if you want, then there are many kind of links and citations that you can follow to get more of a complete view. Okay, so where shall we start? Well, let's, as a good talk always does, let's start with some equations. So remember, those of you who did DARA Unit 1, a couple of equations. So on the left-hand side here, we've got the Planck equation, and for radio astronomy, because h nu upon kt is very much less than 1, this approximates to this equation here, which is, as we all know, the Rayleigh-Jeans equation. So this basically tells us that the brightness as a function of temperature of a black body will approximate in the radio domain to this value here. So we can work out how bright things are. And then also, if we want to measure the flux density of something with a radio telescope, then our flux density S nu is equal to B nu, the brightness, times the solid angle that the object subtends. So back in the 1920s and the 1930s, these 2 equations kind of explain why no one ever thought that radio astronomy would ever find anything at all. Because everyone thought that radio astronomy, the only thing it would be good for would be to look at stars. Stars don't actually emit very much in the way of radio waves because they're quite hot objects. The sun has a photospheric temperature of 5,800 Kelvin, and also stars are very small objects. So if we were to think about a star like the sun at a distance of 1 parsec, and we wanted to observe it at a frequency of 1 gigahertz, well, firstly, its solid angle would be incredibly small, 10 to the minus 15 of a steradian. And then also, it wouldn't be very bright because we're in the radio regime. So we're talking about the important quantity in the Rayleigh-Jeans equation is the ratio of the frequency squared to the speed of light squared. And for radio waves, that's quite small. It's only about 10. So if you take these into account and you work out what the flux density of a star at 1 parsec would be, it would only be 0.3 microjanskys. And that's very small. And remember, a Jansky is a very, very small unit itself. And now we're talking about 10 to the minus 6 of a Jansky, and we're talking about a star like the sun, and we're talking about something that's, you know, as close to the sun as we ever get. So astronomers basically thought that stars were completely undetectable in radio waves, and there would never be anything else in the Milky Way that you would see in radio waves. So nobody expected to find anything. So nobody looked really, until we got to this guy in the start of the 1930s, Carl Jansky. And this is really the birth of radio astronomy. So Jansky was an engineer. He worked for the Bell telephone labs. And when they were doing wireless telephony, they realized that there was actually a mysterious source of noise in the telephone signals. And so Jansky built his telescope on the left here himself. This is the days of radio astronomy where if you wanted to do an experiment and you built the experiment yourself and you carried out the experiment. So here's Jansky's telescope. Here you can see these wheels, and these are car wheels from a Model T Ford. So he mounted his telescope on car wheels, which I thought was quite cool. And then he looked at where you saw this noise in the sky over the course of a year. And what Jansky found is that the noise basically moved around as the Earth moved around the sun. So the noise was coming from a position in space. And more than that, it repeated every 24 hours. Well, almost every 24 hours, repeated every 23 hours and 56 minutes, which, as you know, is the sidereal day. So initially, Jansky thought he'd detected the sun, but because the emission came around once every 23 hours and 56 minutes, he pretty soon realized that this was radio emission from the Milky Way. And this was at a frequency of 20 megahertz. So I said in the early days of radio astronomy, we didn't even get pictures. This is Jansky himself on the right with his apparatus for recording the data. And it recorded on basically a strip of paper with a moving pen. And what we got was a bunch of wiggly lines depending on the brightness versus time of the radio emission. And then here you can see his screen where using a bit of chalk, he's drawn the sky and the constellations. And this is the strips as his telescope scans across the sky in a drift scan mode. And you can see that lo and behold, this is the plane of the Milky Way, because we can see this constellation here that he's drawn on, which is the constellation Cassiopeia. So this is what Jansky called star noise, because still at this point in history, all astronomers thought that the radio waves were coming from stars. So about another, here is some data from Jansky's paper, which was published in the Proceedings of Radio Engineers. There were no astronomy radio papers yet, and here you can see his individual strips taken at various times, showing how the noise goes up and down over time. So now we move on to the 1940s, and this is really the first image of the Milky Way that we get, and it's the first dedicated dish for radio astronomy. And this was done by an amateur astronomer, an engineer, another telephone engineer called Reber, and he built in his backyard his own radio telescope. He thought he would do one better than Jansky, and that he would increase the frequency, because if you observed at a higher frequency, then you were more likely to detect things. Because if you're looking for thermal emission, like that equation I showed you a couple of slides ago, then the higher the frequency, the brighter the emission. nu squared over c squared, remember. So if you make nu larger, nu squared over c squared is larger, and so the flux density should be larger. So initially, he went to the highest frequency that he could build a receiver for, which was about 2 and a bit gigahertz. But he found absolutely nothing at all, even though based on Jansky's results and scaling up, he should have quite easily detected things. So he then went and rebuilt his system to work at a lower frequency. And eventually, after another couple of iterations, he built a receiver system that worked at 120 megahertz, and he detected what he called cosmic static. And there are 3 sources that he found in his survey of the sky: Cassiopeia, source in the constellation Cassiopeia, source in the constellation Cygnus, and another source in the constellation Sagittarius. So we know now that only 2 of these are in the Milky Way, Sagittarius A and Cassiopeia A, and the third one, Cygnus A, is actually a radio galaxy. The other thing that I should say here is that all of these sources are called A. Convention in these days, the very early days of radio astronomy, was that because people only ever expected to find a handful of radio sources on the sky, they decided that they would call them after the constellation, but then just put A for the first source discovered, B for the second source discovered, and so on. Pretty quickly, radio astronomers realized that was a really stupid way of naming sources, and no sources were ever called B. After the first sources were discovered in constellations, they decided to shift to different ways of naming things that were based upon coordinates and names of telescopes rather than the names of constellations and letters of the alphabet. The other thing, the important thing that Reber discovered is that he expected that the radio sources would be thermal, they would follow a black body, and that wasn't the case because he didn't see anything at higher frequencies. So the important thing that Reber discovered is that what these radio astronomers were seeing at these frequencies was non-thermal emission, which was a bit of a surprise. Nobody expected to see this. And then the other little anecdote that I found when I was researching this seminar about Reber's observations is that very nearly this paper that he wrote, which was eventually published in the Astrophysical Journal, it was very nearly rejected by the editor because Reber was an engineer. He built his own telescope. He put lots of engineering terminology and words in his paper. And at that time, there were no radio astronomers. So the editor of the journal had no referees that he could send this paper to who had ever done any radio astronomy before. So nobody knew how to referee the paper. And so the editor very nearly rejected the paper, which I think would have been a real shame for the very first image of our Milky Way in radio wavelengths if the paper had been rejected because it was so new that nobody understood it. Okay, so from Reber, we go to the very first identification of what these radio sources are. So remember that everybody thought that they were stars. And the problem with these radio telescopes, early radio telescopes, is their angular resolutions were degrees. So you could not match up the radio emission from your radio telescope to a star or to a nebula. It was very, very difficult. So we had to wait until 1947. And this was done by an Australian called John Bolton. And he took one of the bright sources that had been found, Taurus A, and he used this crazy technique called C-cliff interferometry that had actually been invented by another engineer, a radar engineer who became an astronomer, Ruby Payne-Scott. So Ruby Payne-Scott is a name that it isn't really on our lips in radio astronomy, but it should be, because Ruby Payne-Scott was the first woman radio astronomer. So she, with a bunch of other people in Australia, helped to pioneer this interferometry technique. And initially, it was to detect, as you can see here, bad guys. So imagine that you have you're in the middle of the Second World War. and you want to find enemy planes coming in, and you've got your aerial, your antenna, and it has a beam that's many degrees across, and you can't localize the direction to the bad guys, to individual planes. Well, if you use a radio antenna or a dish that's located on a cliff, then you can turn this into a simple 2-element interferometer. So you are emitting a radar wave to the plane, which could either be directly reflected back to you straight away, or it could be reflected back from the majestic sea. So you have 2 paths and a path difference, and you can make an interference fringe. And with the interference fringe, you can work out where this thing is more accurately. So what John Bolton did is he used a sea cliff interferometer in Australia to locate the position of Taurus A. Here are the fringes that he got from the interferometer, and it turned out that Taurus A wasn't associated with a star. It was associated with this object here, which we call the Crab Nebula. So a supernova that exploded somewhere around 1000 AD. So this is the very first time that we knew what these radio sources in the Milky Way were, and we know that at least some of them were associated with supernovae and things like the Crab Nebula. Now we move on a little bit later to certainly for Milky Way studies of star formation, which is what I'm most interested in, are H2 regions. And this is the first discovery of radio H2 regions by Westerhout in the late 1950s. So Westerhout made a survey of the Milky Way using this telescope here, which is a 25-meter at Dwingelo in the Netherlands. This isn't the original telescope, by the way. This is now a historic monument in the Netherlands, and it was restored to working capability in 2000. And on the left-hand side, we have Westerhout's survey of the Milky Way, covering the plane of the Milky Way here, and another region around Orion over here. So this was quite a groundbreaking study at the time. No one had done this. This was the highest angular resolution study that had been carried out. I say highest angular resolution. The full width half maximum of the beam was just under 0.6 of a degree. So we're well away from arc-second resolution here. But with this resolution and working at a frequency of 1.4 gigahertz, Westerhout found 82 sources in the galactic plane, 56 of which of them are thermal sources, like the ones that we originally thought we'd find, and 35 of those were associated with optical nebulae. So this is quite a good result. We can start seeing what these radio sources are, and we can see that they're H2 regions, like you would see in an optical image. So here's an example of quite a well-known set of regions. This is Westerhout's original discovery image here of 3 regions in his catalogue. His catalogue is called the Westerhout catalogue, and everything in there gets a number ranging from 1 to 82. So it's a little bit like the Messier catalogue, but for radio regions. And these regions here are W3, 4, and 5. And this is quite a well-known complex of H2 regions in the Milky Way called the Heart and Soul nebulae. On the right-hand side, we can see what these look like in the mid-infrared from the WISE satellite. And they are large H2 regions. The radio emission will fill these cavities here. And there are massive star clusters in the center of these cavities, ionizing the gas, and the gas emits radiation through Bremsstrahlung, and we see that in our radio telescope. So many of the regions that we see today are called W something, and that's because of the original Westerhout survey. So things like W51, W49, and here W3, 4, and 5. Okay, so these were the first radio H2 regions. Right, so this kind of completes my early historical survey. What I'm going to do now is kind of move to surveys that were done much later, still using some of the same principles. I haven't talked about surveys with interferometers yet, except for the C-cliff interferometer. But really, as radio astronomy developed and we got steerable interferometers with many dishes, our capability to make images got much better. And so surveys of the Milky Way with interferometers became a thing. But there are really two types of radio surveys of the Milky Way. And they really allow you to do different kinds of science. So surveys with single dishes, like these three dishes at the top here, the Effelsberg 100 meter, the Parkes 64 meter, and the Jodrell, the Lovell telescope here. The angular resolution of these telescopes is low. So really what you're looking at is large-scale diffuse emission from the Milky Way. But because you are observing with what we call a filled aperture telescope, so the full aperture of the telescope is completely filled with steel and is a complete mirror, then you have a good surface brightness sensitivity. So it's really good to pick up large-scale diffuse emission. Things like large H2 regions, like Westerhout found, supernova remnants, like Taurus A or the Crab Nebula, or other kinds of objects. You're also the surface brightness sensitivity is very good for spectroscopy as well. So in particular, if you want to look for H1, then at large scales, then you want to use a single dish, basically. Interferometers are a different thing. The apertures are not filled, and so we know with our interferometer that it acts like a spatial filter on our image, and it filters out this large-scale structure. So we don't get the large-scale structure in an interferometer survey of the Milky Way. What we get instead are compact, small objects. So if you're looking for very small H2 regions, like ultracompact H2 regions, and these are very young H2 regions, only about 100,000 years old, then an interferometer is absolutely perfect for that, because it actually helps you in a way, because you cut out all of the diffuse, fluffy emission that you don't care about. You have high angular resolution, but low brightness, surface brightness sensitivity. And so if you're looking for compact H2 regions, radio stars, background radio galaxies, then these are the kinds of instruments that you want to use. And many of the Milky Way surveys have been carried out with this guy here on the left, which is the Very Large Array. And we'll come on to some of the surveys that have been done with the Very Large Array. And we'll also come on to some of the surveys that are done with this guy on the right, which is the MeerKAT telescope. So if you are a black belt ninja at CASA and interferometry reduction, then you can combine the two together. And this is a very powerful technique, because the filled aperture here, the single dish, fills in the UV plane for you, or rather the hole in the middle of the UV plane, and you can then make a survey that is sensitive to both large-scale emission and small-scale emission. However, you do need to have some extreme skills at interferometry reduction, because you need to be able to combine small single-dish data and interferometer data in the Fourier plane, and decide upon the appropriate weights for each one of those. So I'm steering clear of that. I'm not such a ninja. Okay, so what I'm going to do is just run through some of the major single dish surveys. And really what I've kind of done is just picked some of them out. It's not complete by any means, but I've picked out some of the ones that are still in use today. And one of those is this survey, which is the Haslam 408 megahertz survey, which was done in the early 1980s. And it's an all-sky survey, so it uses the Parkes, the Jodrell and the Effelsberg telescopes. And this small inset image here is the image from Haslam's 1981 paper. And you can see here, this is what the state of the art of graphics was in the 1980s in publications, because most everything was published as contour maps, because color printing was certainly not as good as it could have been in those days. Haslam's map is still in use today for large area studies, things like the cosmic microwave background, and in particular removing the galaxy from the cosmic microwave background as a foreground. And so Haslam's data has been translated into kind of more modern heel picks, and here's a projection, an all-sky projection of the Haslam map. What you're seeing here is diffuse synchrotron emission from the Milky Way. So this is a kind of low-density gas excited by supernovae and radiating at low frequencies. Moving up in frequency, another single dish is this one, and I've chosen this because I'm sure that many of you know the guy that did it, Justin Jonas, who's taught a number of you in DARA units 2 and 3, and you'll know him because he's also the chief engineer of MeerKAT. And every time I meet Justin, Justin reminds me that he started out studying the Milky Way. And so I thought it would be nice to include a slide to show Justin's contribution, which is this 2.3 gigahertz all-sky map with HartRAO. And this was quite groundbreaking when it was done. There was no all-sky map at these frequencies in the southern hemisphere. So this was the very first one. We'll come back to MeerKAT and MeerKAT's contributions in a few slides' time. Okay, just let me check how I'm doing for time. Oh, probably well over time. Melvin, if you need me to stop, just or speed up, please tell me. Okay, so finishing up the single dish surveys, I want to look at the best one, which is this survey, which is called CHIPASS. And this was done with the H1 multi-beam receiver on Parkes, which is a little bit like a radio wavelength camera with 21 pixels. And so this is the best 1.4 gigahertz single dish survey on the market at the moment. It has a resolution of 14 arc minutes and a sensitivity in brightness temperature of about 40 millikelvin. And if you want to find out more about this, then I recommend going to this link and checking out the survey. You can get the data from there in a variety of formats. You can also get the survey paper too. But what does the future hold for single dish surveys? Well, this is probably the premier survey of the future. So this telescope here is FAST, the 500 meter spherical aperture telescope in China. And they are planning a drift scan survey with FAST. And FAST can access a region of the sky from minus 14 declination to plus 66 in declination. And as you can see here on this plot on the right, that covers a nice chunk of the Milky Way. Unfortunately, it doesn't cover many of the interesting regions of the Milky Way, which are located in the southern hemisphere. And so I leave it as an exercise for you to persuade the politicians to build the 500 meter aperture telescope in southern Africa. Good luck. Okay, so but this will perhaps be the ultimate single dish survey of the Milky Way. It will be higher resolution, only 3 arc minutes compared to CHIPASS at 14 arc minutes, and with really fantastic sensitivity. It's a spectroscopic survey. The channel width of the survey are 7.6 kilohertz, and in a single channel, it will have an RMS sensitivity of about 1 to 1.5 millijanskys. So this will be super good when it's done. Moving on to the interferometry, and again, I've only picked out a few of the interferometry surveys. One of which, and kind of the one of the first ones, is this survey at 1.4 gigahertz, the VGLA Galactic Plane survey, which was later kind of combined with the Canadian Galactic Plane survey, CGPS, the Southern Galactic Plane Survey, SGPS, to form something called IGPS, which is the International Galactic Plane Survey. So this was a pointed survey using a configuration of the VLA that results in a resolution of about 1 arc-minute at 1.4 gigahertz, and the RMS noise of this survey is about 1.8 millijansky. So the main aim of the VLA GPS was H1 mapping, but there's a lot of continuum science you can do with it. So here's a couple of examples of studies that were done with the VGPS. So on the left here, we have a supernova remnant, and the VGPS emission is given by the contours. And then this grayscale here is molecular gas and carbon monoxide. And so here what we're seeing is a supernova remnant that's impacting on a molecular cloud. And you can quite clearly see here that the molecular cloud follows the morphology of the supernova remnant. And so what we might be seeing here is a shock compression of the cloud and possible triggering of star formation. On the right-hand side here, we have a plot of supernova remnants from the green catalogue, and many of these were picked from the VGPS, as this arc-minute resolution survey was good enough to resolve many of them. Okay, so moving on to something I know is dear to Melvin's heart, is another interferometric survey, which is something called CORNISH. CORNISH, I think, in the history of Milky Way surveys, has got probably one of the best acronyms that's been invented, possibly one of the most contrived acronyms, but certainly I think one of the best. So CORNISH stands for the Coordinated Radio and Infrared Survey for High Mass Star Formation. And the aim of CORNISH, I should say it's called CORNISH because Melvin is a proud Cornish man, and so was the other survey PI. The aim of CORNISH was to get radio data here on the left-hand side with the VLA that was of matching resolution to this infrared imaging data in the middle from the Spitzer Space Telescope. And so you could coordinate and match the two together to identify things like ultracompact H2 regions, planetary nebulae, or radio stars. So we're jumping up quite a lot compared to the VLA Galactic Plane Survey in resolution. CORNISH has an angular resolution of 1.5 arc seconds. And this is because it was done, well, for two reasons really. It was done with a more extended configuration of the VLA, what's called the B configuration, and it was also done at higher frequency, and at a frequency of 5 gigahertz. So we have a survey of a chunk of the Milky Way. So here's our view of top-down view of the Milky Way, and this wedge here shows you the region that CORNISH was observed over, and it's really very sensitive, down to a sensitivity of somewhere between 0.2 to 0.4 millijanskys. So looking at the sources in CORNISH and using an automated source finder, the CORNISH team found over 2,600 reliable sources. These are all sources that are brighter than 7 sigma, and they found many hundreds of ultracompact H2 regions and planetary nebulae and radio stars, and I have to say, you know, probably 1,000 or so radio galaxies too. So let me show you some of the sources that CORNISH found. Here, comparing the CORNISH image on the left to the mid-infrared image from Spitzer, the GLIPS survey in the middle, and then the near-infrared. This is from the UKIDS survey in the JHK bands here. So this object in the top row is a cometary H2 region, and you can see that the shape of the cometary H2 region in radio is quite similar to the shape in the mid-infrared. And that's because the 5 gigahertz emission here is quite well it's tracing the ionized gas and also the 8 micron emission shown in glimpse, in one of the glimpse bands, is also shows you pretty much where the ionized gas is. It has many lines of polycyclic aromatic hydrocarbons, or PAHs, and they show up very nicely in the photon-dominated regions just outside the H2 region. So we see these, and lots of the H2 regions, as Melvin will tell you, probably all of them are shaped like cometries, and they're probably showing where there's a bow shock, where the emission, the expansion of the H2 region is being stopped by the molecular cloud, which is kind of found here at the head of the comet. CORNISH also saw many planetary nebulae, and here's a candidate. They don't show up too brightly in the near infrared, but you see them in the mid infrared, and they look like stars in 5 gigahertz. There's also, or maybe slightly extended stars at 5 gigahertz. They're also very compact objects, which again show up in the mid infrared and the near infrared, and these are radio stars. And on the next slide, I can show you another example of a radio star. So here's a radio star that has very red infrared colors. And we also see things that don't show up in the mid-infrared and the near-infrared. And these are probably radio galaxies where the infrared surveys are not deep enough to pick up the infrared emission from the galaxy. So we see them in the radio, but don't see them in the infrared. And here's an example where we see two components. Possibly this could be 2 galaxies close to each other, or just a chance alignment. Okay, so the nice thing about CORNISH, and the thing that I was particularly most interested in, and I'm sure Melvin too, is what are called ultracompact H2 regions. These are very, very small H2 regions, only, say, a few 100,000 years old. And here's an example. This is a multi-wavelength image of basically a complex of 2 H2 regions. We have a cometary H2 region here, and then an unresolved H2 region at the head of the comet. The grey contours here are a submillimeter continuum, which is showing you where molecular hydrogen is. And then the background colours are mid-infrared emission from glimpse. So here what we're seeing is embedded massive star formation that's deep within a molecular cloud. And the best way to find this is in the radio. And CORNISH, being sensitive down to around 0.2, 0.4 millijanskys, it's sensitive enough to detect these H2 regions essentially anywhere in the Milky Way. So here's another top-down plot of the Milky Way. And on this side here, we can see CORNISH. This is from a paper by James MeerKAT. And James plotted all of the CORNISH ultracompact H2 regions and all the other massive star-forming regions found in other surveys on top of the artist's impression. And it kind of shows that most of these things line up with the spiral arms. But the sensitivity of CORNISH means you can pick out ultracompact H2 regions way over here in the Milky Way. So we know that we found all of the ultracompacts. There may be fainter classes of objects that are even smaller and optically thick, and we're in the process of carrying out surveys to find these using the VLA at higher frequency. Then I should also advertise that not only do we have CORNISH in the Northern Hemisphere, there's also a companion survey called CORNISH South, which was carried out with the Australia Telescope Compact Array. And I know that Melvin is busily looking through all the 3,000 sources and making sure that they're all real, and weeding out all the side lobes and the artifacts as we probably speak. Okay, so moving on from CORNISH, there's another interferometry survey called MAGPIS. And MAGPIS is a bit of a survey of surveys. Here is another image of a large H2 region from MAGPIS. It's a 1.4 gigahertz survey. It doesn't cover the whole plane of the Milky Way, but because it combines observations made with different VLA configurations, the B and the C and the D configuration, it has good sensitivity to large structures and is very good at picking out supernova remnants. And if you want to find out more information about MAGPIS, then here is the MAGPIS website. So to show you another example of a MAGPIS image, here is a combined radio and infrared image to show you how you can pick out H2 regions and supernova remnants. So remembering that H2 regions are thermal and supernova remnants are non-thermal, well, with an H2 region, you'd expect to pick it up in the infrared too, but you wouldn't expect to pick up a supernova remnant in the infrared. So the objects that, this image is coded, so the objects that have radio and infrared show up in grey, and the objects that don't have infrared show up in these kind of pastel colours here. So these are our supernova remnants here, and these are our H2 regions. So one of the scientific aims of MAGPIS was to make a more complete catalogue of supernova remnants. There's a lot more that you can do with MAGPIS, and the data is available and useful. Very kind of quickly, this is one of the new surveys where the results are just coming out and being published. This is GLOSTAR, a global view of star formation in the Milky Way. It's another, it's basically like CORNISH. Covers pretty much the same area, but it's a little bit deeper and it's a bit lower resolution. So the image on the top here, this has a resolution of 18 arc seconds, about a sensitivity of, I think this is not the full survey, because the number I got from the paper was 45 microjanskys, but I'm noticing on the grayscale here, this is not quite 45 microjanskys. But this is the, I've taken this plot from the GLOSTAR paper, and because it shows you an important point about doing surveys with interferometers. So this bottom plot here is a plot of the background noise. And in an interferometer survey, various regions of the survey are limited, they're noise limited or dynamic range limited, where you have bright objects. Because you're using an interferometer, which doesn't have a full UV coverage, where you get one of these bright supernova remnants here, that translates into a region of high noise, because you're limited by the dynamic range in the image. And so you can't image faint objects near to bright objects. So this is one of the great things that MeerKAT will help us with, because if you have greater UV coverage, you can come out with a better dynamic range, and so we'll be less limited around bright objects. Okay, excuse me a moment while I just take a quick drink. Okay, so what I wanted to finish with was the real new kid on the block, and what is a real game changer for studies of the Milky Way. The MeerKAT has more antennas than any other dish interferometer in the world. And what's important for an interferometer is the number of antennas, because the more antennas you have, the more baselines you have. The more baselines, the more antenna pairs you have, the better the UV coverage. And that means you get much better imaging, and you get a much greater image fidelity. And that's important in the Milky Way, because as you can see here, this is the MeerKAT galactic center image, which is absolutely stunning, I have to say. But image fidelity is really important in the Milky Way, because the Milky Way is a very complex and messy region of the sky. We see many different kinds of objects, all packed in close together with very, very complex structures. And so if you want to image these complex structures very well, we need a lot of baselines. And so MeerKAT is going to be a real game changer. SKA is going to be an even better game changer for the Milky Way. It will be challenging because doing the imaging in these complex regions does require CASA black belt ninjas, so it will take time to make these images, but when we make them, they will be fabulous. The other thing about MeerKAT is not only does it have lots of antennas, which mean more baselines, It has a very broad bandwidth, so 800 megahertz of bandwidth at 1.4 gigahertz frequency. So this means we get extreme sensitivity. And you can see this in this galactic center image, which it shows things here that we didn't really know what they were. So all of these filaments in the image, they've been seen before in VLA images, but not at this angular resolution, and also not as many of them. MeerKAT discovered many, many more filaments than were seen in the VLA images of the galactic center. Things like these supernova remnants, you can see the large ones, but you can also see smaller regions. And one of the things we're really hoping that MeerKAT will be able to do is to find the youngest supernovae in our galaxy. Supernovae that have exploded, maybe within our lifetimes, but we haven't seen them because they're located on the far side of the galaxy. And the visible wavelength light from the supernova was blocked by dust clouds in between. Okay, so moving on from the galactic center image, we also have more data from MeerKAT. It turns out that over the last sort of year or so, MeerKAT has been carrying out a galactic plane survey effectively in spare time. So when the galactic plane is visible, there's been a program to observe the galactic plane at 1.4 gigahertz, and this has collected basically enough data to cover roughly the inner third and a bit of the Milky Way. So in terms of galactic longitude, it covers the southern Milky Way from a longitude of 270 up to the edge of the Cornish region at a longitude of 60 degrees. So this is a huge survey of the Milky Way. It's 3 terabytes of reduced data, and I couldn't even think what the raw data was like. And as I just told you, MeerKAT has got great angular resolution and great sensitivity. So the angular resolution of this survey is 8 arc seconds and a sensitivity of about 15 microjanskys. So this is easily an order of magnitude deeper than anything that we've ever done in a Milky Way survey before. We're working on this at the moment, and we have a preliminary catalogue that MeerKAT has found over 300,000 sources in the Milky Way, but this is still a work in progress. The data is still embargoed to within the survey consortium, but I can show you some sneak peeks as long as you promise not to tell anyone else. You'll note that I've carefully removed all of the coordinates from the images that I'm going to show you. This will not be a presentation like the cosmic microwave background presentation, where somebody took a screenshot of somebody's presentation and published a paper on it. Okay, so this is a chunk of the Milky Way that we can see with MeerKAT on the left-hand side, and then the best current survey on the right-hand side. This is a survey of the Milky Way that was taken with the Malonglo telescope in Australia at a frequency of 840 megahertz or so. And then this is a corresponding image with MeerKAT. So you can see there's just so much more structure. All of the things that look blurry in here are much less blurry in the MeerKAT image. We're also seeing many, many more point sources in this image, and resolving much better structure of these H2 regions and supernova remnants. And we have really good surface brightness sensitivity in this MeerKAT image. It's not great. You can see that there are kind of undulations or peaks and troughs in the background, and that's caused because of the lack of sensitivity on large scales. But you can see that there's many of these filamentary structures in the wider Milky Way, which have not really been seen in previous imaging. And you can also see it around here. This is what I talked about, dynamic range. So here's a very bright radio galaxy, and you can see in the Malonglo image there's a lot of artifacts around here, and in the MeerKAT image these artifacts are much reduced. and we can pick out point sources around these radio galaxies that we wouldn't see, we haven't seen before. Here's another example. This is a stellar example. So this is an evolved a massive star called a luminous blue variable. And these things are sort of throwing off shells of emission. And so we can see this really nicely in our MeerKAT image. And then, but if we were to look at it in our Malunglo image, it just looks like a blob. So there is no way you'd figure this out to be a luminous blue variable. And there are many more of these in the MeerKAT data. And finally, the filaments. We see a lot of filaments in MeerKAT, and we're still in the process of trying to figure out what they are because nobody expected to find them. They're like the things in the galactic center. They're much more widespread. And we think, well, that most of the ones we've looked at so far tend to be non-thermal structures. We think they might be tracing magnetic fields, but we are still cataloging all of them in the plane of the Milky Way and trying to figure out exactly what they are by relating them to other objects like supernova remnants and H2 regions. And then talking about H2 regions, again, something that's dear to my own heart, which is triggered star formation. And here's an H2 region from the MeerKAT image. And then this is a multi-wavelength image. So here in blue is the radio emission from the H2 region. And then here is Atlas Gal or mid-infrared emission showing you molecular clouds and star formation around the edge of the H2 region, which is presumably triggered by the expansion of the H2 region into the surrounding material. Okay, so it's been a bit of a whistle-stop tour through the Milky Way. I've broken Melvin's time limit of 40 minutes, but I hope that's okay. And let me just quickly summarize. There's a lot of history of Milky Way studies, a lot of previous work that's been done. The science has ranged from the birth of stars to the death of stars to the life of stars in radio stars. One of the things I'd like you to take home is that new facilities drive new science. So people like Jansky and Reber, who built new facilities, admittedly mostly in their backyards, they were able to do new science. So new facilities like MeerKAT and SKA will result in new science and new discoveries. MeerKAT is here now and is turning out data. I should also say that quite a few DARA advanced students and ex-DARA students are working on this data. And the future for studies of the Milky Way is, I think, is bright, and there's certainly a lot to do. There's more data to look at than anyone can look at. And so there are a lot of studies that can be carried out. And we still have the SKA to come and the benefits of that. So I shall stop there and take questions.
Yeah, thanks very much, Mark. That's a real excellent tour of the Radio Milky Way for us. And the historical perspective is really great too. So well done on that. And yeah, several of the DARA-related students who are going to be working on the data are actually on the seminar. So Mavis is with us, and Calvin's, who we hope to get underway at TUK in Kenya, is here. And and I see Yara, who will be also working on some of this as well. So it's good to have those with us. Also, Willis will be starting his postdoc in South Africa, looking at some of these sources in the galactic plane as well. So, so there's a good future coming for DARA students on this as well. Okay, so we have one question in the Q&A at the moment. Please feel free to put some more in there, anything you like. So first question is from Dennis Salongwe. Let me allow Dennis to ask his question. So Dennis, I've unmuted you. Do you want to ask your question, if you can?
very much for the presentation, Mark. I just want you to share more, shed more light on why a single dish and superconducting is. Thank you.
Did you catch that, Mark?
You broke up a little bit, Dennis. I guess well, I've got your question on the Q&A, and I think if it's the same one you asked about why we use a single dish.
Exactly.
Yeah. Okay. So we use a single dish really because of sensitivity to large-scale structure. So if you're interested in things like old H2 regions, which could be degrees in size, or supernova remnants, which again could be many tens of arc minutes or degrees, it's much better to use a single dish because firstly, your imaging will recover all of the large-scale structure, and then also if you wanted to do some science by measuring the total flux of the object, then the single dish will measure the total flux, whereas the interferometer doesn't, because it filters out the flux on large scales. So that's why we use single dishes. The drawback, of course, is that the angular resolution is low unless you can persuade somebody to build you a 500-meter dish.
Thank you very much, Mark.
That's right, Dennis. It's good to hear your voice again.
Thank you.
Yeah, there are plenty of old friends on this talk. Next up is another one. Isaac, I know you said you're happy for me to ask it, but I'll unmute you and we'll see if we can hear you. If not, I'll ask for you. Go ahead, Isaac.
Hi, Mark. Can you hear me?
Yes, I can, Isaac.
My question is, what's one most anticipated thing about the Milky Way that, in terms of continuum, that's probably going to be answered by the SKA, or that astronomers are looking forward to be answered by the SKA? I know there are several, but maybe what's the one most anticipated? Thanks.
Sure. Okay, so continuum. Well, in a way, I think we almost forget H2 regions because H2 regions are fantastically bright for SKA. The Jansky source is huge for the SKA. I think the kinds of objects that are so faint that we can't see them at the moment are really what the continuum questions are about, and that's probably radio stars. So we know of quite a few stars now that emit radio emission, and some of these are have been detected, but some of them are have not. But what the SKA will allow us to do will be to make a distance-limited survey of radio stars out to several hundreds of parsecs. So that's certainly one question that could be answered. I have to say also that the SETI Search for Extraterrestrial Intelligence community are also interested in Milky Way surveys because they realise that you can cover many billions of stars by looking at the radio emission from the Milky Way. So they have contacted me in the past and asked about various projects I've been involved in, whether it would be possible to use the SETI engine at the same time as taking the data. So
thanks.
Stars and aliens, probably.
Thank you.
And these radio filaments, because they're very faint too, and we don't understand what they are.
Yeah, I was going to follow up myself with, from what you've seen in the MeerKAT survey to date, and you've mentioned the filaments as being unusual, but I know you can't show pictures or talk much about it, but is there anything else that really stood out so far that just seems unusual?
Not yet. I mean, that luminous variable looked unusual because it just it was just almost a perfect circle, so it kind of leaped out at me when I was looking through the images. there are some objects that are very, very complicated and that we haven't figured out yet. They look a bit like jellyfish. I think they are possibly pulsar winged nebulae, maybe, or some kind of bright rimmed globule that's showing up in radio emission, or interacting galaxy. I don't know.
Yeah, you need the multi-wavelengths though to find out.
Yeah.
Yeah.
And there's certainly a lot of faint point sources.
Yeah. It sounds like Carvins is keen to get started on his masters straight away because he's asking if you can share the presentation. Well, one thing, Carvins, is we will, as usual with these talks, we will make the recording available, so you can watch the slides back through that way. But if you actually want the PowerPoint, I'm sure Mark would be happy to pass it on. Probably, maybe yep. Removing any sensitive MeerKAT.
Any sensitive information could be removed. Yes.
Calvin's might remove the boxes that you put in to cover up the coordinates. You could send a PDF, that would be fine.
Yeah.
Okay. Okay, we've got some more questions now. Good. Got an anonymous attendee, so I don't know who's asked the question, so maybe that means I have to ask it. Well, that follows on nicely. So the person's asking about these filamentary structures, and is there a reason why you were not expecting to find them?
Yes, there was. The reason is that people have looked for them before, and they've only found them in the galactic center. So there have been a number of VLA studies by, trying to remember the name of the guy that's done them. That will come to me, I'm sure. Sorry, Melvin?
Yusuf Sadeh, he did the Galactic Center one.
Oh, yeah, Yusuf Sadeh, yes. So he's been kind of instrumental in the studies of these filaments so far, using the VLA. And so they've shown up in the VLA images only in the galactic center. And Yusuf Sadeh looked outside the galactic center and didn't find any. And so the paradox has always been, what are these things, these filamentary structures, and why are they only found in the galactic center? And lots of the models that have been developed to explain them essentially rely upon the intense cosmic ray flux from the center of the Milky Way. And this cosmic ray flux illuminates electrons, or provides high energy electrons, which spiral around magnetic fields in the center of the Milky Way and show up as these filaments. So the models kind of suggest that we only see them in the Milky Way, the center of the Milky Way, because of the cosmic ray flux there. So it was a real surprise to see them in the MeerKAT images, because we didn't expect them, and we only see them because of the fidelity of the MeerKAT images and the sensitivity. In those Malonglo images, you can see things that you might have suggested might have been filaments, but also might be PDRs. But in the MeerKAT image, we do quite clearly see very kind of linear structures throughout the Milky Way. So that's why we didn't expect to see them, because no one had seen them before.
Would you also expect the magnetic field to be stronger in the galactic center than the rest of the?
Yeah. I mean, there's another theory as well, which is that, well, there's a couple of theories, one of which I don't hold much truck to. There's the one theory is that there are a population of unseen millisecond pulsars, and we're seeing synchrotron jets from the pulsars. And then there's another theory, which is that particularly the bright ones are seen near Sagittarius A star are cosmic strings.
Interesting.
That's an extraordinary claim, which I always think that extraordinary claims require extraordinary evidence.
Yeah. Okay. Carvins has a science question this time. So Carvins, do you want to ask your science question? I've unmuted you, I think.
Yes.
Go ahead.
Yes. Okay, despite, okay, thank you first for the presentation. I have a question on these two, I think the H2 region and the planetary nebulae. I think they have similar characteristics at infrared and the radio wavelengths, but I would like to know the difference, or which method can you use to distinguish between the two?
Okay, Calvin, that's a good question. It's not a question, it's not my particular area of expertise, but my understanding is that you can use the shape of the object for one. And then you're right that the infrared colors can be similar, but I think the far infrared colors can be different. And so by using Herschel data, you can determine what's a planetary nebula and what's, say, for example, a compact H2 region. We don't expect planetary nebulae to be embedded in molecular clouds because they're old evolved stars. So if you see something that's seen against a molecular cloud, it's more likely to be an H2 region.
Yeah, and in the Cornish survey, then my previous PhD student, Tanya Urbor from Nigeria, she was distinguishing the PN and the H2 region mostly through the colors in the infrared. So that's quite easy. And your compatriot, Vivian Otieno, is at the moment, she's doing a master's here at Leeds with me and is developing machine learning, CNN type learning to actually do this automatically. So we're trying this to see if we can automatically distinguish all these different types of objects that we see in the plane surveys with using neural network, convolutional neural network techniques, which we're about to find out if it works because she's coming to the end of her thesis. So.
Thank you.
Okay, Denelza, you've had your hand up and you have a question, so go for it. Denelza, do you want to ask your question?
Okay. Hi, everyone.
Hi, Denelza.
Hello. Thanks for the tour about the radio astronomy in the Milky Way. I have sent my question in the question and answers, but I will put here. We know that there is coming the SKA and the MeerKAT and others are doing their best in studying the Milky Way and other regions, okay? And also we know that the science cases of these equipments are huge and we are waiting, at least me, for big surprises, okay? I would like to know, in your point of view, what do you think it will be the top result of these equipments?
Oh, okay, Denelza, that's again a very good question. Do you mean the top discovery in the Milky Way?
Yes.
That's a very good question. It's probably one I don't know. I'm sure we will see things that we didn't know existed. For me personally, it's not so much about the continuum science. It's more about the spectroscopy. Because I guess one of the things I didn't really say is that in the Milky Way, when you go to very, very faint fluxes, most of the objects you find are background radio galaxies. And personally, I'm not very interested in them. And as it turns out, the extragalactic astronomers are frightened of the Milky Way and don't want to look at these galaxies either. So the top discovery for me is probably spectroscopy and things like radio recombination lines, which are very, very faint lines, but with the SKA, it will become a routine machine for doing spectroscopy of plasmas like H2 regions. And we can do a lot of modeling for that. And then again, I think as I said earlier, radio stars, that we can really go down to very faint fluxes and look for radio emission from main sequence stars. Okay. I don't know, Melvin, did you want to add anything? What do you think the top, except aliens possibly?
Yeah, I mean, you're probably right about the unknown, because I think at this massive leap in sensitivity and resolution, we will just see things we've never seen before. Maybe new types of interacting binary star that might turn out to be quite interesting, perhaps. But for me, I think, yeah, the recombination lines on jets and that kind of thing, I think. So, we can see the jets at the moment in the continuum very well, but coupling that with the kinematics to see how they kind of are driven and spiral around, that would be a big step forward, I think. And it's something I wrote about 10 years ago, before when we were first starting about the SKA. So I'd be quite happy to see that.
And another thing's just occurred to me, which will get a really, really good view of star formation in young stellar clusters. We'd be able to study them at very high angular resolution. We'll be able to measure the proper motions, the radio proper motions. When you're looking at a young stellar cluster, sometimes you can only pick up young stellar objects by radio flares, and we will be able to get a very, very detailed view of the 3D structure of young stellar clusters that we don't have at the moment.
Okay.
Yeah, and actually the sort of top science case that is driving the design at the moment is actually looking at sort of planet formation. So as well as star formation, we'll start looking at planet formation itself as well. So that's the new exciting field in radio astronomy here as well. Okay, Nai from Madagascar has been there for a while. I've seen that question. Then we'll finish up with Nchimi. So Nai, do you want to? I don't know if I'm pronouncing your name correctly. Sorry about that. Oh, we got two Nais as well. So Nai Avo, do you want to ask your question?
Yeah, can you hear me?
Yep.
Yep. Yeah.
Hi, Mark. Hi, everyone. So I just have a random question. Which part or which study in particular of the Milky Way are we focusing right now at this moment?
That's good. Again, a good question. So, well, I mean, for me, kind of personally, I'm always someone who likes to study all of it, which is a very poor answer, I know. I mean, the reason I like to do Milky Way surveys is really for to obtain a kind of a complete statistical sample of objects. So a lot of my work is involved in samples, looking at as much of the Milky Way as we can. So with MeerKAT in particular, we're looking at the inner third of the Milky Way. So if I can share my screen again and show you what it basically looks like. I tried to do a plot of the MeerKAT survey, but the problem with Galactic Plane surveys is the aspect ratio is too big to put on a presentation. So let me share my screen. Okay, right, make it big. Okay, so on the right-hand plot, which is the top-down view of the Milky Way, we're kind of looking at this region that's shaded a little bit further out in this direction. That's the region we're looking at. It includes parts of the center of the galaxy and the galactic bar, and this will be interesting to look at with MeerKAT because there's quite a bit of star formation that seems to occur at the ends of the bar. And also these spiral arms as well. So that's a particular region of the Milky Way that we're looking at. I also have a soft spot for a region as well that's called G305, which is in the MeerKAT survey, and I'm looking forward to I'm looking forward to taking a look at that in the MeerKAT data, because it's absolutely full of H2 regions.
Yeah.
Okay. Thank you.
Thanks, Niver.
You're welcome.
Yeah, G305 is very busy in Cornish South, I can tell you as well. I keep revisiting it. Okay, and Chimi, seems suitable for you to bring up the last of the questions. So, Chimi, do you want to ask your question? It's a very good one.
Yes. Good morning, Mark. Good evening, Mark. Good evening, everybody. Can you hear me?
Yep.
Ken and Jimmy?
Yeah. Okay. So I was just wondering how the density. Well, you didn't cover this, but it was just something that came up when we talked about magnetic fields. How the density of the of cosmic rays at the center of the Milky Way galaxy, how the density of the cosmic rays compare with when you are out in the interstellar space. I would imagine that influences the magnetic field dynamics there.
Yeah, well, it's a good question. I don't know the exact numbers, but I do know that the density of cosmic rays in the galactic center is very much higher than the density of cosmic rays around the sun. The problem that we have is we can never really trace cosmic rays back to their source, because as they propagate through the Milky Way, they get kind of turned around by the magnetic fields. So by the time these cosmic rays reach the Earth, they effectively come from everywhere. So we can't directly look at the center of the galaxy and see that there's a greater number of cosmic rays coming from there. We have to do it by theoretical modeling, or looking with different traces, like some molecular lines are affected by the cosmic ray density. But certainly it's, I'd have to look at the exact number, but it's maybe factors of 100 more than it is at the position of the sun in the Milky Way.
Thank you.
It's good to hear you again, Chimi.
Sure, always great. I can assure you Zambia misses you too.
Excellent.
Oh, well, thanks everyone. It's been really good to keep in touch again and to hear everybody's voices and see everyone on the line. So I think that's been good. We've had our hour and a half, which is what we normally do. So certainly remains for me to thank Mark on behalf of everybody from the audience for a really good talk and a really excellent set of discussion around the questions. Many thanks, Mark. We certainly, I think are really looking forward to a new golden age of kind of galactic radio astronomy, but just galactic astronomy in general, of course, because we have the Gaia satellite operating at the moment with new results about to come out in the end of this year. So we'll have accurate positions for all of these billions of stars, and combining that with the radio emission from the stars that's a whole new ball game in stellar radio studies, I think. So there's just a huge amount of this kind of big data type work where you've got these huge surveys with hundreds of thousands of objects. It's a very exciting time. So lots of scope for sort of masters and PhD projects for people coming up through the DARA program. So I think it's a really good time to look forward to. Okay, so I think that concludes what we need to do for today. I'll just put up a closing slide to tell you about the upcoming seminar. Oh yeah, sorry, I need to tell you about it first. Let me find about it. Yeah, so our next one is on the 7th of October. So that's going to be Bernard Asabare from Ghana, who's been on secondment in the Netherlands for a number of years now, working with the LOFAR telescope, which is a very low frequency radio telescope. So we've heard a lot about sort of dish radio astronomy today and in previous talks, but Bernard will tell us more about this very sort of different type of low frequency radio telescope. So very much the type of forerunner to the bit of the SKA that's going to be in Australia. So that will be, you know, something a little bit different for us as well. Okay, so that's coming up on the 7th of October. So keep your eye out for that one. Okay, so I'll just put up the closing slide and thank everybody again for watching. We'll see you next time.
Thank you all. It has been a pleasure.
Thank you.
Thank you.